Good afternoon. Welcome to the EPA ROAR Research Project, sampling for critical rare earth metals in acid mine drainage, presented by Bette Conway. Bette she is a licensed professional geologist working for EPA Region 3 Water Division. She is the lead reviewer and technical expert for Clean Water Act coal mine permitting. She has a bachelor's in science of geology, mineralogy, and hydrology from Indiana University, Bloomington.
The other Indiana.
She has worked as an environmental scientist at EPA for 17 years, and in her spare time, she creates custom handmade jewelry using precious and semi-precious stones, fossils, and carat/gold silver. Please join me in welcoming Bette.
Thank you very much. So I've been interested in metals, obviously, for a long time. But previous to coming to EPA, I worked in private industry. I was a consultant, a landfill director, coal mine inspector. So I've worn several hats in the past. And it was great to have this opportunity to do this ROAR project of Shamokin. This is the main creek that runs through Shamokin. My ROAR proposal was sampling for critical minerals in acid mine drainage and the coal refuse around Shamokin, in the hopes that it would provide information to inform long-term mine pool treatment and land reclamation. This shows where Shamokin is relative to the rest of Pennsylvania and has my statement that this is my opinions, not necessarily those of the agency or DOE. We worked with DOE on this project. I'll explain more about that later. What is the ROAR program? It's a program in our Office of Research and Development that anyone within the agency can make a proposal about. We need to know more about this thing. And I knew from serving on the national mining team that we were starting to look at critical minerals table, and they include the lanthanids as well as scandium and yttrium. I have another slide that has all of them. I can't memorize all of them. They are considered critical due to their national importance and vulnerable supply chains. We know there's quantities of critical minerals in coal regions, but we don't know how much and where, and more importantly, how they migrate through material, particularly like coal refuse areas. There are the 17 rare earths. So our project was to identify quantities of rare earth elements in acid mine drainage and the coal refuse. And then we wanted to take that data and evaluate it using a USGS water quality model. It's called FREAK AMD, that identifies the optimal critical mineral extraction and treatment strategies. And then OSM has a model for long-term operation and maintenance cost for any acid mine drainage facility. So we used both of these programs to evaluate our data sets at the end of the project. And then we also developed a publicly available toolkit. I'll note that Shamokin has a very good public website of all their resources, and we'd like to see other communities do that. So we put together a general toolkit of resources, and we use Shamokin as an example. We want to establish best practices for evaluation of treatment technologies and for analysis. As you'll see in here, we got a little different results on our refuse, probably by the different lab methods utilized to determine if there were critical minerals present. So I've kind of covered the first phase. We sampled the acid mine drainage from 5 of the largest discharges in Shamokin Creek watershed. And that data indicated that all 15 rare earths were present in the acid mine drainage and associated sediments. Our second phase of this sampling effort was to look at the large coal refuse areas. And initially, we proposed to cone and quarter our sample efforts. That basically means we would go collect samples from several areas. We would pour one sample on top of another out of plastic bags into a tall cone, and then we would split that 4 ways. But realistically, when we got out on these sites, you're limited to where you can sample on a big coal refuse pile. I'm sure most of you know that. When you're walking out, the sides are pretty dangerous. You could slide down easily, get engulfed in the coal. So we were really limited. A lot of these coal deposits were up on the mountainsides surrounding Shamokin. So we kind of scrapped that idea and collected it in a large 2-gallon bag, a sample, mixed it in plastic ware that we decontaminated between each sample, and we mixed it very thoroughly, and then we split it 4 ways. We gave some to Penn State, we have some left over for the community and the coal mining company, and paid up. And I should also note that all of our results will be listed on Department of Energy's public website of results. They have a repository. If you're not familiar with that, they have a library that you can go and look up information on AMD sampling and coal and other materials that they have funded. So this is the sampling naming key we used. We looked at Big Mountain, Scott Ridge. These are all areas surrounding Shamokin, Excelsior, Henry Clay, Cameron, and the Trevorton pile. And this is a picture of the Trevorton pile in the background. This was deposited by building wooden ramps and over 200 years of coal being deposited up on here. This watershed, this immediate area, Trevorton, the town of Trevorton, isn't even in a mining area. It's just this got taken over from other, the adjacent watershed and deposited there. And there's probably, we estimate, 17 to 23 million tons of coal in that pile. So this kind of is a close-up of Shamokin and the areas that we sampled around the community. I put this in because in the acid mine drainage sampling effort, I want you to notice the Big Mountain mine had the lowest pH, 3.74. And I think the test results bear out, that we found a lot more at Big Mountain, probably because it hadn't had a chance to oxidize yet. Some of the areas were not as readily accessible. Maybe we had to go several hundred feet down from the source, from the deep mine. So it had a chance to do some oxidation, and the pH got up to 5 and 6. And in those, we still found critical rare earths, but not in the quantity that might be available there had we been closer to the source. The Big Mountain AMD sample, as I mentioned, had the lowest pH and the highest concentrations in water, 47 to 48 micrograms per liter. It also had the highest concentrations in nickel and cobalt. Total RE concentrations were about 4 to 52 parts per billion. Henry, Clay, Sterling, and Cameron wet sediment samples, and what that was is the colloidal material that starts dropping out. If you've seen acid mine drainage when it's coming out, the red colloidal material that's coming out, we collected all those wet sediment samples to see what was in there as well. So this represents what we found in those. They were slightly elevated to the North American shale reference. And you can see what we found in the wet sediments there. The data sets include characterization results for acid mine drainage and associated sediments. We'll be delivering those to the town of Shamokin soon. Again, they were from 14 water samples and sediment solid samples, and we did filtered and unfiltered samples. Department of Energy was very interested in this project, and they joined us for some of the activity, particularly the refuse sampling, and it was very helpful to have them along to kind of figure out where we should sample. As I said, it was very hard to traverse these big refuse piles, so we kind of started looking for what we thought might be migration pathways for rare earth elements, knowing that they're likely more in the partings and other material. I think some follow-up projects that could be done out there is looking at maybe some of the breakers in the area and looking at the reject material for critical minerals. But I will note, on one of our sites, on Trevorton, Department of Energy grabbed a water sample at the base of the coal pile, and it had a pH of about 3, and there was close to a part per million total rare earth elements in that sample. So obviously things are migrating down through these piles and concentrating with the acid. So here's our water samples. You can see that the top line is Big Mountain. It had quite a bit more than the others. The others kind of follow a similar curve. There's the sediment results. And that was Henry Sterling clay, which again, that discharge goes down, I think, a covered ditch and goes under a highway. So where we could first sample it was probably a couple 100 feet down. So there was probably a lot more material in the sediments because of that. And this is just the total REEs for all the sites. So again, Big Mountain had 15 REs detected in the dissolve phase. We also found cerium, which is an important rare earth used in several applications, I think including in battery manufacturing. I may be wrong about that. I want to take a moment to thank people that participated in our study. Chuck Ravata worked with us. We built on his database that he sampled these areas back in 1999, 2000, and we built on that information that he had. Barbara Arnold of Penn State, we gave her some samples to analyze of the refuse material. And Dan Corey, he's retired now, but he worked with PADEP in the Pottsville office. Penn State sample results. Let's see. So Penn State ran samples of refuse material from all of the refuse sites, Trevorton, Cameron, Excelsior, and Big Mountain. And we did, as I mentioned, we split those samples with DOE, Nettle Labs, Penn State, and PADEP. Water and AMD data was evaluated by Tetra Tech using the USGS and OSM software programs. In our final report, we will have a cost estimate for long-term operations and maintenance in the initial construction of treatment facilities at each of those large acid mine drainage discharges. And we've already begun, well, we've pretty much wound up work on the technical toolkit of resources. This will all be coming out soon and presented to the community. I think a picture tells a lot of the story here. So I've got quite a few pictures here in the last part of this. Big Mountain, you're close to the source of where it wells up. That's pretty close to where it's welling up out of the ground. And that's where we sampled. And we sampled at the top of the mountain in Big Mountain. Big Mountain was more of a mix of rock, overburden material along with the coal, where some of the other piles were much better sorted. For example, Trevorton is almost pure anthracite coal. So we limited our sampling to the upper reach of Big Mountain because the lower bench at Big Mountain had been so reworked and mixed and people had dumped trash there, and we didn't want to include that in the sampling. We felt that it might provide some interference in our results. There we are at the top of Big Mountain. We used a field XRF that was calibrated to look for critical minerals. We're testing the viability of these to be used as a screening device in the field to identify areas where you might find critical minerals. You see us looking at one there. One of these rock samples tested pretty high on the XRF, and DOE took that sample and they're doing a 3D mapping of it to see where secondary mineralization may have occurred and what insights we can get from this piece of overburden material. And they took several other samples as well that they plan to eventually provide results on. So there's the Big Mountain refuse results, 207 parts per million to 278. And then the total, if you add in yttrium, 228 to 310. This is the Trevorton refuse pile. I don't know if it shows up very well. See these rainbow colored areas down in the bottom of the picture? You could tell where there was redox zones within these giant piles and that things were moving. So we did concentrate some of our sampling on those areas. And the water sample I mentioned previously, you see one pond in the far right corner. There was actually another pond behind this pile. This pile is like 100 feet tall. This is several hundred feet tall. And back behind it was another pond that we sampled, or DOE sampled, and we found the part per million results of total REEs. Trevorton results from the Whole rock, I would say there it was probably mainly coal. 142 to 265 parts per million. And then with yttrium included, it's 157 to 295 parts per million. Cameron, Glen Burn, you can see the deposit is up on the top of the mountain. There used to be a colliery that took the reject material and dumped it on top of the mountain. So it was very hard to traverse this area. There was only certain benches we could get out on to get a sample. This is the Cameron Glen Burn area. This is the one I said kind of goes a couple hundred feet down and goes under a highway. And you can see all of the colloidal material that's dropping out there and why we had such higher results in the wet sediment samples at this location. And there's the Cameron refuse results, 115 to 324 parts per million. Then with whole rock, it went up to 342 parts per million. Okay, this is the Excelsior refuse. This is an interesting area. There's a giant pile, and it doesn't look very big in this picture, but if you're driving along that highway, it's just immediately adjacent to the road, and it's a couple hundred feet high. And across the road, that long pond, the pond has two stages. I was told by one of the local people that went out with us that there were two deep mine shafts or two different seams that well up in these ponds, and you'll see in my pictures a little difference in the coloration from those. Right above that pond is an old coarse refuse area that's been reclaimed. So you can see the coloration in those two ponds and those two areas that were upwelling into the pond. So we sampled both of those to see if there was any difference and make a comparison. We also sampled at the spillway that goes into the adjacent creek. And this is the Excelsior refuse pile. That gives you a better idea. That's the road in the picture on the right at the bottom. And we were trying to sample in drainage ways. That's Matt Norapel of the agency. He's using the XRF to check for critical minerals in the waste. So Penn State's Excelsior refuse results were 228 to 278 parts per million, with yttrium 254 to 306 parts per million. So this is a summary of all those results. And I would acknowledge these are not exceedingly high. These are probably mid-range values, probably, as compared to some other sites. Maybe a little higher, but the good news is that they're there. They could help offset costs of reclamation of the area. That was the reason I wrote this ROAR proposal. We wanted to find out if they were there enough so that it could offset costs for treatment and maybe even reclamation of the refuse areas. So this is a summary of what we found. And our analyses came in fairly recently, and ours were about 20% lower. And we think it's because we didn't use the same method to prep the samples as Penn State did. I think all of us are still, the laboratories are still figuring out test methods for this material. So this is a good to know. The difference in analysis, Penn State ground, ashed, and then digested the samples. We did not ash the samples prior to. But we don't think it's a point of heterogeneity. I'm not going to be able to say that. Heterogeneity in the sample because we mixed the sample so well, and it was pretty much 20% difference all the way across the board. So that's sort of indicative of maybe the test method made a difference. We also didn't measure scandium in the refuse. Oh, I got through that pretty quick, didn't I? Thank you. But some key points I want to leave with you on this is what makes projects out in a place like Shamokin more viable is just the sheer amount of carbon material that's left there. I have the opportunity to sit in on a lot of meetings with Department of Energy and others on critical minerals. And what's driving a lot of the projects that are getting funding is the amount of coal that's available and the carbon material. Because there are a lot of proposals to make different things out of it. I was very fortunate a few weeks ago to be asked by Senator Chris Dush of Pennsylvania to tour Penn State's critical minerals extraction facility. I'm happy to say they've patented the process and got it to where it's ready to take to a production scale. One interesting note is on the higher end in the pH, when they got up to I think 6 to 7, a little higher, they're able to, through their process, separate cobalt and manganese, which is really important for people doing battery manufacturing. They want that cobalt separated from the manganese. So that was very beneficial, you know, that they figured that out in their process and they're getting ready to take it to large scale production. The other thing I heard in this tour of the facility, there was a company along that has recently purchased the Tunnelton mine, which is in central Pennsylvania, and they're experimenting with making jet fuel out of the coal waste, which from what I understand is it's an older technology, but I'm sure they're using more modern applications of that technology. But they plan to extract critical minerals at the same time, and they're taking in fracking waste. We already have an NPDES permit before us right now that we're reviewing for just the fracking portion of that project. But it's very exciting news. I think Senator Dush envisions, you know, if they can put together the investment, that there'll be quite a bit of reclamation across Pennsylvania and extraction of critical minerals at the same time, because Pennsylvania is very unique in having all this coal waste. Because I talk to the western states all the time in the national mining team, and they don't have any places like this where there's so much material concentrated on the surface. Most of the hard rock mines out west are, you know, very separated spatially. They don't have good infrastructure to get in or out. And there are coal mines out west, but not as numerous as here, obviously. So with that, thank you, and I'm happy to take questions. I probably whistled through that too quick. I'm not checking the time, but if anybody has any questions, I'm happy to entertain. Yes?
Would you say that you've only scratched the surface as far as identifying potential source piles, or do you think you have a pretty decent idea of ability to exclude some of them from?
I think we're just in the initial phases. I mean, Department of Energy has done several tests out there. They're using drones to do 3D mapping of the coal piles, and they're looking for areas where those critical minerals might be migrating through the coal pile. Trevorton, again, is an excellent example. We found highly concentrated REEs in a pond at the base of that pile, so we know it's moving through there, but there's a lot of follow-up study to be done. There isn't much data on this. I'm not sure if there was much anthracite data before we did this sampling several years ago, and others are starting to build on that. And again, I mentioned that DOE is keeping a repository of all that information, which is a good thing for everyone, you know, to be able to reference. Yes?
So a number of refuse piles are burnt. So in Glen Burn, for example, there's a number of burning refuse piles, underground mine fires. Would you sample any of the red dog or the earth refuse and analyze it separately? And if so, how does the heat and oxidation of the refuse change the concentrations of the rare earth elements?
We did not sample any red dog areas. We didn't really visually see many red dog areas around Shamokin in our field. I'm looking at the Shamokin representative. Can you think of any around there offhand?
The areas that you went to and sampled, there are some areas in the western part of Coe Township
Okay.
where we've seen some smoke and steam coming up from the ground, but not the Coleman. So the Glen Burn, and you could drive down, look at that bank, and you'd see steam and smoke rising, but especially on rainy days, you'd really see that coming up. And I haven't seen that in quite a while now. So I don't know if it's burned itself out or gone deeper. I'm not sure, but it doesn't surface as much as it used to.
But that's definitely an area for further study. I will note that, you know, there's a lot of companies looking at coal ash too, which is good. They've found critical minerals in it. But the thing is, once it's been burnt and has that glassy, you know, glass-like structure around it, you've got to take the pH back down to get the critical minerals out and break that up somehow, where if you're just taking it right out of acid mine drainage, it's a much easier process. Coal refuse, I think, will be an easier process as well, but that remains to be seen. We're just starting to sample those types of materials. But definitely, I think when you go back and look at some of the photos, like the one I had of Trevorton, where you can see these redox zones within the pile, that we could find concentrated areas of critical minerals in some of these huge piles. Yeah.
Two questions. One, you mentioned some of the piles are mostly coal waste, coal refuse, and some are kind of a mix of both urban and coal waste. Is there a trend with the rare earth element concentrations in the composition of the pile? And B, did you get good data from the XRF and useful data from the XRF?
With the XRF, we didn't get, we sampled anywhere we got a hit with the XRF. I will say that. I think we're still kind of evaluating that. Like I mentioned, DOE is 3D mapping one sample that was exceedingly elevated on the XRF to see if it was secondary mineralization. And they're trying to map that out and figure out how that formed. So I think there's room for a lot more study in that area. And you asked me another question. The difference in the piles. Well, let's see. If we go back to, can I go back? Let's see. Trevorton was almost pure coal. We'll just look at EPA's results. Trevorton and Big Mountain weren't that much different, really. But Trevorton was almost pure coal. I mean, they're mining, they've got silt dams at the bottom of this huge pile that they are letting dry out. They excavate it and they sell it to Ukraine on the spot market as pure anthracite product. So there wasn't much waste rock in that pile at all, whereas Big Mountain was really a mix of material. Parts of Cameron were more pure, and then you found a real mix of things. I think it depends on how old it was and when the colliery was there and how they deposited the material. Because I think at one point in time there was a colliery at Big Mountain as well as Cameron and some of the other areas. Which I'm sure you're all familiar with that. I wasn't until I worked up there, but it's a big processing building where they sort out the coal and then the reject material goes up on the hill. They're pretty amazing. Old facilities, but you don't see many of them anymore. You had a question, sir?
What concentration of rare earths is considered economically viable?
Now, see, that's a $50 billion question.
You got to be this concentration for it to actually be viable.
Well, several points on that. One, our knowledge base on what's in these materials is, pretty new, and we're learning and trying to add data to that. So I don't think we know how much that'll vary within the coal piles. Two, the economics of all this is changing so rapidly. I heard last week in the news that China imposed a tariff on critical minerals to the U.S., and we're running out of places to get it. And the low-hanging fruit, the easiest place to get it is from old abandoned mine waste, both hard rock and coal here in the United States. That's the easiest place to get the critical minerals. I feel I can say that with some confidence. There's been other ideas floated. Like I know NASA was working on some projects to mine portions of the moon for critical minerals. Imagine how much that would cost. Or we could do deep ocean exploration. EPA is actually issuing emergency exploration permits off the coast of California, between California and Hawaii. But I don't think a lot of the big companies are really interested in that because it's pretty risky. We don't really have the technology. If you guys remember that sub imploding a few years ago, I don't think we really have the technology to do a lot of deep sea mining yet. I think it's an area that's growing rapidly, but again, the low-hanging fruit is the mining waste that are all over this country, both hard rock and coal. I will mention that the chemistry of acid mine drainage from a copper mine versus a coal mine is pretty similar. You'd be surprised, pretty close to the same elements. So I think there's room for more study and more testing and analysis. But that's going to, how much it's worth is going to change drastically in the next few years based on where can we get it as a country? Are we getting it from other countries? Are we mining it from the moon? All those are variables.
I just kind of to add to that, I can send you a presentation that does have that number if you're thinking about that, but it's way higher than what we're seeing. I mean, it's like grams. But to build on that's point, like the incentive to recover the stuff from mine drain just isn't high. Because if that was, then we'd have industry already doing it, right? If it comes to a matter of national security where like, the government decides that okay, we absolutely need to do it, we can't keep importing it from others, we're gonna dump money into doing this, right? Then it becomes some type of government incentive to push this stuff. So I think that's kind of the hold off. Like, I don't think we're ever gonna find like some mine drainage treatment or mine drainage discharge that's just so rich in rare elements that we go to the shop. How important is this stuff for our country? How much is the government going to do that? Whether it's treatment credits or offset.
And I think there is a lot of interest, for national security reasons. I mean, there's been several executive orders signed recently, both for anthracite and other material, other coal materials. There's several funding opportunities available through Department of Energy. If you've not checked out their website, they have a lot of money to spend on research for projects like this. And I think it's going to come down to you have a process where you're removing it from the acid mine drainage, you're removing it from the refuse while you're processing that material to make something else. I've seen everything from carbon brick to asphalt, shingle materials to jet fuel. So I think there's a lot of opportunity, but it'll be a combination of things. And one thing that weighs positively for Pennsylvania is just the sheer amount of material laying around.
I think one thing when we think about these rare earth elements, we think about renewable energy technologies and cell phones and stuff. But I was at a Feds Only workshop last year, and there was someone from the Department of Defense there that was like up in arms because they had a shortage of antimony, which is a major product in ammunition. And like, I don't know, during COVID, China stopped exporting it to us, and the United States was like running out of antimony to make their own munitions. They were starting to lose crap. It's like basically like, if we don't figure this out, then when it gets to the point that we need this stuff, then the Department of Defense is going to go and scorch earth and rip this shit out of the ground, regardless of the time. So I'm getting ahead of that.
So again, I think the cost is, the value is going to change drastically in the next few years as we're cut off from other countries and obtaining it ourselves. And there's interest in making battery plants here in Pennsylvania. Senator Chris Dush is pushing very hard on wanting to have full battery manufacturing facilities in Pennsylvania.
Investors are pushing for people to invest in USA, what's it called, Rare Earth. It's a publicly traded company that is, I guess, in close discussions with the Trump administration.
There's one running in Mountain Pass, a rare earth mine.
In Mountain Pass.
California.
That's about the only.
That's the only one I know.
Yeah, I was going to say that's the only one, and there is a huge lithium deposit in the Salton Sea, but that's all depositional, washed in, so they could mine this. I think they estimated, we were at the same meeting, I think they estimated there is more lithium in the Salton Sea than currently in vehicles currently used throughout the entire United States right now.
Well, there's a lot of lithium in the brine that comes up out of the geothermal areas near the Salton Sea that they're using for energy production. And that ends up in the Salton Sea. There's lots of people looking at recovering that lithium.
There we go. So I think all of these type of projects are going to be a combination effort, building on whatever processes deposited that material previously and then reworking it and utilizing the materials. So the big win I didn't mention is the water quality is going to drastically improve when these type of projects happen. And I think that would be a great thing for Pennsylvania. Over 60% of their streams are impaired by acid mine drainage. So that's why I'm so excited about this project. Any other questions? No? I thank you for your time.